Alright, today we're going to talk about triangle proportionality theorems and how we can use properties of triangles to solve for missing pieces of the triangle. So the first thing we want to talk about is the triangle proportionality theorem. So every theorem has two parts. There's a premise or an if part and then a conclusion. So the premise of this is if a line parallel to one side of a triangle intersects the other two sides, and here's the conclusion, then it divides the sides proportionally. So it's kind of wordy, so let's go ahead and translate all these words into symbols down here. So we're going to use this triangle, triangle that kind of has two triangles in it, to translate this into symbols. So if the line TU, or the segment TU, is parallel to QS, so those two horizontal lines are parallel, then it chops up my triangle proportionally, which means that RT is going to be, the ratio of RT to TQ is going to be proportional to RU to US. So looking at the picture just means that these two chunks of triangle that have been created by that extra parallel line, they're going to be proportional to each other. So the next thing we're going to talk about is the converse of the triangle proportionality theorem. Now, a converse of a theorem is basically just the opposite. So I'm going to hit pause, fill this in, and then we will talk about what it is. All right, if a line divides two sides of a triangle proportionally, then it is parallel to the third side. So let's go ahead and write an if-then statement in symbols for this theorem. What this is saying is that if I start with the proportionality of the ratio of RT to TQ being proportional to RU to US, if I know those are proportional, then I know that TU is going to be parallel to QS. Okay? So based on the proportionality, I can prove that those two lines are going to be parallel to each other. So you can use either kind of version of this, the triangle proportionality theorem, or its converse to help you prove some important things about triangles. So let's go ahead and use these theorems to find the value of our missing variables. So in A, we have two lines that are parallel to each other down here, which based on our triangle proportionality theorem tells us that the two chunks on each side are going to be proportional to each other. Okay, so let's go ahead and write out the proportionality statements here. This means that 16 to 12 is going to be proportional to 20 to y. Okay, once I've set up that equation, it's just a simple matter of solving the proportion. So I get 16y equals 240. Divide both sides by 16. And y is equal to 15. Okay. So let's go ahead and do the same thing with the next example. So again, I have these two parallel lines, which means that they're chopping my triangle into proportional pieces. So I know that x is to 10 as 4 is to 8. Then I can cross multiply. 8x equals 40, divide both sides by 8, and get that x equals 5. All right, let's look at C. We've got the same thing going on with C, but it is going to be a little bit trickier. We're going to have one extra step. So I have two parallel lines, so I'm going to be able to set up a proportion, but I actually need to do a little bit of extra work before I set up the proportion, because I need to know what is this length FE right here. I know that the entire height of the triangle is 14, and I know that this upper piece is Z, which means that this little blue piece right here, that's going to be 14 minus whatever Z is. Okay. So let's use that to set up a proportion. Since those two lines are parallel, I know that Z to 14 minus Z has to be proportional to 15 over 6. Then I'm going to go ahead and cross multiply. So I get 6z is equal to 15 times 14 minus z. Now I've got to do some distributing. So 15 times 14 is going to be 210 minus 15z. Now I need to get my z's to the same side of the equation, so I'm going to go ahead and add 15z to both sides. So 21z is equal to 210. I'll divide both sides by 10 to get z equals 10, and that is my missing side length. Okay, so this one was a little bit lengthier, and you did have an extra step here. I'm going to show you one other way to work through the same exact problem. I'm going to do it over here in red. So I know that those two parallel lines at the bottom mean that I'm going to be chopping my triangle proportionally. So instead of looking at each chunk separately, I can look at the chunk of the smaller triangle and compare it to the chunk of the larger triangle. So for example, my vertical side length, the proportional statement I would set up, or the ratio would be z to 14. So the height of my smaller triangle over the height of my big triangle. On the other side, on my kind of diagonal side, I've got to do the diagonal length of the smaller triangle, which is 15, over the entire length. So that entire length right there is going to be 21. 15 plus 6 is 21. Then I can go ahead and do my cross multiplying. 21z is equal to 210. Divide both sides by 21, and you'll get z equals 10 again. So same answer, different way of working through it. And both are valid ways. So whichever way kind of works with your thinking better, I would recommend using that. Okay. So let's go ahead and look at these next examples. Here what we're going to do is we are going to determine whether two lines in our triangle are parallel. I don't know why this is a P there. That should have the parallel sign. So I'm trying to figure out if BE, I'm just going to go ahead and highlight these in blue, is parallel to CD. So here, since I'm trying to prove that they're parallel, what I'm looking for is, I'm looking to see if their associated chunks are proportional to each other. So what I want to know is, if I look at the proportion on the left side of the triangle, 10 to 16, is that the same as the proportion on the right side of the triangle of 9 to 12? And 10 to 16, I can simplify that fraction to 5 over 8. And 9 to 12, I can simplify that fraction to 3/4. Since 5/8 is not the same thing as 3/4, it means that those two lines are not parallel. And that is by the converse of the triangle proportionality theorem. Let's look at the next one. Again, we're trying to see if our two diagonal lines, the BE and the CD, are parallel. So I'm going to set up some proportions. Here's the proportions for the top of the triangle. 24 to 32. That should be the same fraction as 21 to 28. So if I divide 24 over 32, divide the top and the bottom by 8, I'm going to get 3/4. If I divide the top and the bottom of this other fraction by 7, I am also going to get 3/4. So since these two fractions are the same, it means that those two side lengths are proportional, which means that BE is parallel to CD. All right, let's go ahead and finish off this proportionality statement here. So again, here we're starting with the fact that we know that these two horizontal lines are proportional. So if we know they're proportional, then we're looking at two lengths. QT is the top, so QT is the smaller length, to QR, so the smaller length to the total length, is congruent to, that should be equal to, not congruent to, equal to SU, this smaller length, and then we need to look at this entire length over here. So SU to SR. Okay. Hopefully that was a good enough explanation for you guys for the triangle proportionality theorem. We're going to talk about the mid-segment of a triangle now. You might want to pause here, go and do some of your homework assignment that's about the triangle proportionality theorems, and then come back and look at the mid-segments with us. Let's begin by talking about what a mid-segment of a triangle is. So a mid-segment is a segment that connects the two midpoints of two sides of a triangle. So if you look down at this picture with this triangle has M, R, N, Q, and P. R is the midpoint on this left side of the triangle, which means that it chops that side right in the middle. Same with N. N chops the side length NP right in half. So the mid-segment is a segment created by connecting those two midpoints. Now the mid-segment theorem tells us something interesting about that mid-segment. First, it tells us that it's parallel to the third side of the triangle. Okay, so I know that RN is parallel to QP. It also tells us that RN is exactly half the length of QP. So if QP is 10, then RN is 5. Let's go ahead and translate this into symbols for us. So if RN is a mid-segment, then we know two things. The first is that RN is parallel to QP. The second, we know that RN, the length of it, is equal to 1/2 times QP. Okay. So we really get two things with this theorem. Let's go ahead and talk about using this theorem. So in the next 4 examples, we're going to be finding the value of the missing variable. So in A, I first am going to prove or talk about why this segment X is the mid-segment. It's the mid-segment because this point on the top chops the top of your triangle into 2 equal pieces, and this point on the bottom chops your triangle into 2 equal pieces. So the segment connecting them is a mid-segment. Okay? Which means that X is exactly half the length of that third side of the triangle. So half of 16 is 8, so X would have to be equal to 8. In B, we can do pretty much the same thing. We know that this line that's 14 is a mid-segment because its endpoints are midpoints. And then we know that this mid-segment is half the length of the bottom, which means that X would have to be twice as long as 14. So X would have to equal 28. Okay. Now in C, we have a similar thing. Instead of showing the mid-segment, proving mid-segments using tallies, we're showing that this blue line that I'm coloring in right now, we know that's the mid-segment because it's chopping both sides of the triangle into equal size pieces. One is size pieces of 7 and one into pieces of size 5. So that means that this 6 is my mid-segment and it's exactly half the length of my base of the triangle. So my base would have to be 12. I want you guys to go ahead and try to do D on your own. Okay, press pause, prove to yourself that that length right here is a mid-segment. And once you do, you'll be able to easily determine that C should be equal to 9 because it's half the length of the other side of the triangle.